All right, our next topic is a different generalization of these intersecting families. So here we are interested in the situation where instead of having intersection of just two members of that system, we want to have an intersection of k members and have some restrictions, right? So here's a theorem by Amos and Sudakov in 2002. All right, so again, P is a prime and L is a subset of numbers from 1 up to P minus 1. So we first talk about the modular version. And K is 2. Right, so we're going to have an intersection of K members. So let F be a family of subsets of 1 up to n such that each member has size not in L modulo P and whenever you take an intersection of K distinct members, that's in L or distinct. Then this set contains a most certain number of them. So what is going to be the natural bound? Well, we take the actually the bound is this. You take a k minus 1 copies of the subsets of size and most s minus 1. Oh no, s, right? So then when you take a subsets intersections of k of them, one of them must have size at most, less than s. So if L happen to be numbers from 0 to I don't think this is tight, but anyway, this is a bound. All right, so here's the proof. So again, let L be the L1 up to LS, and let F0 be F. We're gonna inductively construct families like F1. Okay, so we're gonna construct these families. So suppose, so for I 1 up to something, if Fi minus 1 is non-empty, then let A1, A2, AD be a maximal subfamily of Fi minus 1 such that, so I want to choose maximal subfamily such that whenever I take the intersection of let's say a few members, whenever I make intersection of some of them, right, so how should I say? And say cardinality is not in L plus PG for all subset of for all J, which is subset of 1 up to D, and J is non-empty. All right, whenever I take intersections, they don't fall into the L and choose maximal. Then what's gonna happen? By the way, why does it exist? Because if I take a single set, then that already satisfies this, right? So therefore, such a subfamily exists. Now, then we know that D so such a subfamily exists, and the cardinality of such a family is at least 1, and at most it cannot be K, because if you intersect K of them, then it will be inside L. Now let let SI be A1 and TI be the intersection of all of them, and let Fi be the Fi minus 1 minus A1, A2, AD. Okay, so this is how we construct Fi. Now, we repeatedly do this, so how far can you repeat this process? Each time we remove at most K minus 1 members from F, right? So the number of steps we can continue is at least this much, right? What I mean is that there is M such that F1, F2, Fm are non-zero, non-empty. All right. I mean, okay, instead of non-empty, maybe the last one could be empty, but S1, T1, S2, T2, SM, TM are defined. That's a better way. All right. And furthermore, here's the property. SI intersection TI is actually, SI is a subset of TI, right? Because, see, A1 is a subset of this thing. So this is not in L plus PZ. And SI and SJ intersection TI. And if J is bigger than I. So this is coming from, this was not in our maximum subfamily A1 up to AD. So SJ, if I take intersection with TI, then that must be inside L plus PZ by the maximality of A1 up to AD, right? Because if this was not in L plus PZ, then we could have chosen it to be inside our family. Is it okay? Okay, I think I have to fix the proof here. So instead, when you choose family here, let me change this wording. Okay, so now I realize where it could go wrong. So the intersection of A j from 1 up to d prime for all d prime less than or equal to d. So this is what we want to write. So previously I wrote that every sub collection have an intersection which is in L plus PZ. But no, actually I only want to care from A1 up to something. A1, A2, right? Intersection of A1, A2, intersection of A1, A2, A3, intersection of A1, A2, A3, A4, up to intersection of A1, A2, A3, up to AD. All these numbers are not in L plus PZ, all right? So if I try to add the last element, then the only condition that is violated is the last condition. There are no other subsets, right? So this implies that intersection of, right? So A1, A2 in AD, and then last step, ASJ is in L plus PZ. All right. So these two conditions are key conditions which allows us to prove that they are linearly independent. But what are they? Now let's construct the polynomials and vectors. So let Si and Ti be the characteristic vectors of Si, Ti respectively in the Fp to the n, right? And that now we do the typical stuff. It doesn't matter whether I choose T or S, but now let me choose T. So that's polynomial. And again, define Fi tilde as a multilinear polynomial obtained from Fi by replacing xj squared to xj for each j. So this allows us to say that Fi tilde x is equal to Fix for all 0, 1 vectors. Now, we claim that Fi, F1, F2, Fm are linearly independent. So if not, then there's a linear combination. Oh, by the way, I put tilde, right? Now, put x to be Sj. Okay, let's choose I such that choose a minimum I such that alpha I is non-zero. All right. Now what's going to happen? Okay, choose minimum j such that alpha j is non-zero. Then let's put the let's put Sj here. Right? So what's going to happen? Well, I can partition it into 3 parts from I0, from 1 up to j minus 1 alpha I Fi tilde Sj plus alpha j j sj tilde plus, and then I is bigger, I is j plus 1 up to m alpha j fj tilde sc. No, not, these are I. All right, now here we need to use the condition. Remember that if j is bigger than I, then sj intersection ti is in this, in L, right? So j is bigger than I. If j is bigger than I, then sj intersection ti, the cardinality of that is in L plus pz. So which means that fi tj is 0. Then, oh, not tj, small tj. So fi tilde tj is 0. So if I is smaller, then it's 0. Oh, so instead of, so, all right, so better way of choosing j is okay, let me let me change this. Instead of choosing minimum, it's maximum, right? So if I choose j to be maximum so that alpha j is 0, then anything here in this side, this will be 0 because of that, because I is smaller. And anything here, this part is 0, right? Because I is bigger than j. So by all of this, what we end up is alpha j fj tilde sj. And this is non-zero because sj intersection tj is not in L plus pz. So that's 0. So this implies that alpha j is 0. Contradiction. Right. So this proves that they are linearly independent. Now, what does that mean? So claim is proved. So therefore, the number of polynomials is sum of the it's the dimension. It's the dimension of the subspace of multilinear polynomial of degree most s with n variables. So that's sum of the n choose I from 0 to s. Now I know that m is n least size of family divided by k minus 1. So f is at most k minus 1 times n choose I. All right. So that's the proof. And similarly, we can prove it for the version without modular condition. So here's the theorem. Again, by the same set of authors. At f, yeah. Okay, so L has size s and k, then is 2, and f, your family of subsets of 1 up to n, such that intersection of any k of them is L in L for all a1 up to ak, for all distinct families in F. Then we claim that size of F is at most k minus 1 times same bound. Note that the previous theorem doesn't imply that, because we don't have a condition about the cardinality of AI, right? So here's slightly, I mean, if we add a condition that cardinality of AI is not in L, then we could probably use previous theorem, because we can choose prime p to be very large, right? Some prime bigger than n. But now we don't have that condition, so it's a little bit slightly different, but the proof technique is the same. So let's say f0 is f, and we again construct the same way. So for I1 up to something, if fi minus 1 is non-empty, then we construct fi like as follows, right? So here's the condition. If A intersection B is in L for all distinct AB in fi minus 1, then take Si to be largest set in fi minus 1, and Ti is also same as Si. So in this case, Si and Ti are the same. And otherwise, so that's one case. We take among all sets, we choose the one with the maximum cardinality. Otherwise, there exists a maximal subfamily of fi minus 1. Let's say a1, a2, ad, such that intersection of ai from, no, not, we cannot use variable I, let's say j, from 1 up to d prime is in L for all d prime from at least 2 to d. And such a thing exists, such a d prime exists because I already assumed that there's some pair AB where the intersection is in L. No, intersection is not in L. That's the assumption. And if I take intersection of k of them, then the intersection will be in L, so D is less than K. So that means, oh, by the way, and now let fi minus 1 is fi minus all these things. Or in the previous case, let fi minus 1 to be fi, no, the other way around, fi equal to fi minus 1 minus si. Alright, so that's it. Oh, I didn't define, in this case, si is a1 and ti is the intersection of all of them, so a1 intersect a2 intersect. It's the same way. Now we have, so we obtain S1 T1, S2 T2. How far can we continue? Because each time we remove at most k minus 1 of them, so where m is at least this much. Now look at the conditions. So SI intersection TI is, the cardinality of SI intersection TI is equal to TI, because this is, in both cases, this is true. And cardinality of SJ intersection TI is what? Well, first of all, I know that this is strictly less than TI because these two things are distinct. And SJ intersection Ti is in so this, or this is an L, right? So the first case happens if Ti was chosen to be just maximum size set. Yeah, so this is when J is bigger than I. All right. Now let's construct the polynomials. So let Fi x to be product of x dot Ti minus Lj. Here we are multiplying only when Lj is less than the cardinality of Ti. All right. Now let's look at the FI-SI. If I put SI, then it's product of SI dot Ti minus Lj, where Aj is less than cardinality of Ti. And this is same as SI intersection Ti minus Lj, and this is same as Ti minus Lj, but Lj is less than Ti, so this is positive, right? It's simple, just it's enough to say non-zero. And Fi-Sj, what is it? So that's gonna be product of Sj intersection Ti minus Lj. Right. Now there are cases, right? So there are cases where actually this is end, because right. So let's consider one case. So if this was the first case, whenever for all pairs the intersection was in L, then Sj was also one of the members of Fi, so this pair was in L, and their intersection is less than Lj, so that's gonna be 0. Or it's a second case, right? Or there's a second case where we chose maximal subfamily satisfying this, then Sj was not chosen to be AD plus 1, so therefore the intersection is in did I make a mistake? Yeah, intersection is not in L. Yeah, we chose right. I hope I didn't make the same mistake there. Yeah, no. Okay, it was correct. Right. So yes. So this number is in L, and the cardinality is strictly less than Ti, so this is 0. Now we define f1 tilde, f2 tilde, fm tilde as before, and then fi tilde si is 0, and fi tilde sj is non-zero, sj is for all. Yes, this is when it says right, and this is enough to prove that they are linearly independent, and they are all multilinear polynomials of degree and most s with n variables, so the number of them is a most sum of this n choose I from 0 to s, and this is at least the size of f divided by k minus 1, so size of f is k minus 1 times the sum of n choose I. Okay, so that's the proof. All right, there are many other interesting variations, and next section we will also see something like this. Okay, something like